Hi, everybody, and welcome to Unit 5, Lesson 2. What we're going to be doing in today's lesson is exploring behaviors of implicit relations. So, in the first lesson, we looked at analyzing the behavior of a function using the first derivative. Today, we're going to look at analyzing the behavior of an implicitly defined function using the first derivative. So, we have two learning targets today. I can determine the location of critical points of an implicitly defined function. So we're going to need to think back and review implicit differentiation today. The second target is I can justify conclusions about the behavior of an implicitly defined function using evidence from its derivatives. So we're going to need to justify our answer using derivatives, just like we did in the first lesson for this unit. So let's start with a little bit of a review of implicit differentiation. As a reminder, this is what's called an implicitly defined function, and we know that it's implicit because y is not isolated. One of the things we are often asked to do when we have an implicitly defined function is we are asked to find the first derivative. And so, for example, in this problem, we are asked to show that the first derivative is equal to this. Now, in order to show this, we need to actually find the first derivative, show all of our work, and make sure that we can get that as our final answer. The good news is here that we have a goal. We know what we're supposed to get. So now it's just a matter of getting there and showing how we did that. So let's start by taking the derivative. So when I take the derivative here, I'm going to do it one term at a time. So the first term here is x squared, which means the derivative would be 2x. The second term here is 4y squared. Now, if your term has a y, you're going to take the derivative, which would be 8y, and then multiply by dy over dx. Then we're going to have our equals. And then on the other side of the equals sign, we're going to have the derivative of 7, which is 0, and then the derivative of 3xy. Now, in order to do the derivative of 3xy, we're going to need to use product rule. So I'm going to copy the first, which is 3x, take the derivative of the second, which is dy over dx, plus copy the second, which is y, take the derivative of the first, which is 3. So just as a reminder that we need to use product rule to find the derivative of that term. Now you'll notice that there's more than one term here that has a dy over dx. We've got a dy over dx here as part of that term, and we have a dy over dx here as part of that term. So what we're going to do next is move both of these terms to the left, and we're going to slide the 2x over to the right. When we do kind of that rearranging, we're going to have 8y times dy over dx minus 3x times dy over dx equals, on the other side, we're going to have the 3y, which is already there, minus 2x. Now we're going to factor out that dy over dx. So if we factor that out of both of these terms, we're going to have dy over dx, and then we're going to have our bracket, and we're going to have 8y minus 3x equals 3y minus 2x. And lastly, we're just going to go ahead and divide. So if we divide, we get dy over dx equals 3y minus 2x all over 8y minus 3x, which it turns out matches what we were supposed to show. And so we know we're done and we did it right. And that is our brief review of implicit differentiation. Now, there's a couple notes that I want to make here. When we do implicit differentiation, dy over dx still tells us the slope of the tangent line. So just because we're doing the derivative a slightly different way, using a slightly different technique, doesn't change what the derivative means. It's still the slope of the tangent line. The critical points, which are one of the pieces of our learning target today, is finding the critical points, are still going to be the places where the derivative is equal to 0 or the derivative is undefined, just like they were in problems where we didn't have to use implicit differentiation. Same thing. And lastly, we've also learned how to find the second derivative using implicit differentiation. So that may come up as part of these problems. It's all going to be kind of mixed and intermingled together when we find that second derivative. Okay, let's go ahead and look at some examples. So, one of the common things and one of the common questions that comes up on the AP test is the idea of a vertical or a horizontal tangent line. A vertical tangent line is a line that is tangent to the graph, and it's going to be vertical when dy over dx is undefined. One thing that we need to remember is that all vertical lines have what we call an undefined slope. So the slope of a vertical line doesn't exist. It's not a number, it's undefined. On this graph, we're going to have vertical tangent lines right here. If you kind of imagine the tangent line to that circle, it's going to be vertical, as well as right here, which if you kind of, again, imagine that tangent line, it's going to be vertical. Now, we are usually asked to find two different things: the points on the graph where the tangent line is vertical. In this case, the points would be the points -2, 0 and +2, 0, as well as the equations of the vertical tangent lines. Now, as a reminder, any vertical line equation has to have an equal sign, and it's going to say x equals. It's going to be x equals -2 and x equals +2. All vertical lines have x equals in the equation. The other thing we're often asked to look for are horizontal tangent lines. And a horizontal tangent line is going to be a place where the derivative is equal to 0. So it's going to be horizontal, which is the opposite direction. In this case, those horizontal tangent lines are going to occur right here at the top and right here at the bottom. Now you'll notice that that's very similar to where we found places where the derivative equals 0 when we talked about this before. In this case, it's just attached to a circle instead of a curve. Now, again, we're often asked to find two different things: the points where the tangent line's horizontal, as well as the equations of those lines. The points are going to be the points 0, 2 and 0, -2, because those are the points on the graph that I circled. And the equations of those lines are going to be y equals 2 and y equals -2. As a reminder, all horizontal lines start with y equals and then some kind of number. I should probably write that down for vertical for you guys as well. They all say x equals and some kind of a number. You may remember when we were younger, we usually use the acronym VUXHOI to remember that vertical lines have an undefined slope and use the variable x, and horizontal lines have a 0 slope and use the variable y. All right, now, since we are finding the places where the derivative is equal to 0 in the case of horizontal tangent lines, or the derivative is undefined in the case of vertical tangent lines, these are also the places where the graph has critical points. So this is all connected to what we've been talking about with critical points. The critical points are going to give us places where the tangent line is vertical or the tangent line is horizontal. So let's consider the curve given by this equation right here, where we know this derivative. Now, we actually proved this was the derivative as our warm-up to review implicit differentiation. And part of the reason I'm telling you what the derivative is here is because on the AP test, for example, they might tell you that so that if you don't know how to find it, you can still do part B of the question because you know what the equation should work out to be. Find the points at which the tangent line to the curve is vertical, and then write the equations of the vertical tangent lines. Now that means that this question has two parts. First, we need to find the points at which the tangent line is vertical. So that's part one. And second, we need to actually write the equations of the vertical tangent lines. Now, I provided a picture here because after we're done doing this algebraically, I want to compare it to the picture of this graph. However, on the AP test, keep in mind, this will not be part of the test. You're just going to do this algebraically. I do think it's really helpful for understanding what we're doing to be able to compare it to the actual picture of the graph. Okay, if I want to find the points at which the tangent line to the curve is vertical, then what I need to do is look for where the derivative, which in this case is dy over dx, is equal to 3y minus 2x over 8y minus 3x. I need to figure out where this is undefined. Now, what you'll notice is that we have a rational expression as our derivative. It's a fraction. This is going to be undefined when the denominator is equal to 0. So I'm not going to look at the numerator here. A fraction is undefined only when the denominator equals 0. That's what's going to make this undefined. Now I'm going to solve. Now you'll notice I have two variables, so it's not going to be possible for me to solve and actually get a number. I'm not going to be able to say like y equals 1 or x equals 2, but I can get one of the variables by itself. So I can do 8y equals 3x, which means I can do y equals 3 over 8x. Now you might be thinking, how can I possibly find a point if I only know that y equals 3 over 8x? Well, what we need to remember is that we have a second equation here that has x's and y's in it. We know this is the relationship between x and y. So the next step is going to be to substitute 3 over 8x into this equation every time you see a y, so that now we have an equation with only one variable. So let me show you an example. So I'm going to keep the x squared, that's going to stay, plus 4, and then instead of y, I'm going to write 3 over 8x squared equals 7 plus 3x, and then instead of y, I'm going to write 3 over 8x. Now I'm going to simplify, so that means that I'm going to get x squared plus 4 times 3 squared is 9, 8 squared is 64, x squared equals 7 plus 3 times 3 is 9 over 8, x squared. Now you'll notice everything here has x's now, and I can group them all together. So 4 times 9, or actually, let me just simplify this. 4 and 64 simplify to make 16. So I'm going to have 1x squared plus 9 over 16x squared, and I'm going to move the other x squared to this side. So minus 9 over 8x squared equals 7. Now, in order to add these together, these fractions, I'm going to need a common denominator. The common denominator is going to be 16. So this is going to be 16 over 16. That's worth 1. We've already got 9 over 16. And this is going to turn into 18 over 16. Just going to add and subtract. So 16 plus 9 gives me 25. Minus 18 gives me 7 over 16. And that's going to be x squared equals 7. Now, in order to solve this, and I need a little bit of extra room here, I apologize that I run out of room a little bit. In order to solve this, I'm just going to divide by 7 over 16, or in other words, multiply by 16 over 7, which means I get x squared equals 16. So if I solve, I get x equals plus or minus 4. There are two solutions. Now, the first part of my instructions here were to find the points at which the line is vertical, the tangent line is vertical. So the points here, there's going to be two of them. One of them has an x coordinate of 4, and the other one has an x coordinate of negative 4. I can find the y's by just plugging them back into this equation where it says y equals 3/8 x. 3/8 times 4 is going to be 3 over 2. And 3/8 times negative 4 is going to be negative 3 over 2. So those are the points at which my tangent line is vertical. And if I want to know the equations of the tangent lines, those are going to be x equals, in this case, it would be positive 4. And in the example for the second point, it would be negative 4. Now, how does this compare to if you actually look at a picture? Well, if you kind of visually examine this picture, the tangent line appears that it's going to be vertical here and here. You can kind of picture that in your head. And that is the place where x is negative 4 and y is approximately negative 1.5 or negative 3 over 2. And then x is positive 4 and y is approximately positive 1.5 or positive 3 over 2. So if you could graph it, which again on the AP test, they're not necessarily going to provide you with a graph. But if you could graph it, it kind of makes sense visually why you would get those values. All right, let's talk about the next example, which says, consider that same exact curve that we were just talking about, find the points at which the line tangent to the curve is horizontal, and then write the equations of the horizontal tangent lines. So there's two parts here. Find the points that are horizontal, and then also write the equations of those lines. So let's start with finding horizontal tangent lines. Tangent lines are going to be horizontal when the derivative, which we know is dy over dx equals 3y minus 2x over 8y minus 3x, is equal to 0. Now, this fraction is going to be equal to 0 when the numerator is equal to 0, not the denominator. And we can also figure that out by just kind of cross multiplying. So 3y minus 2x times 1 gives us 3y minus 2x. And 8y minus 3x times 0 gives you 0. Once again, you can't solve to find the exact value of x or y, but you can get an equation. So if we solve this, we get 3y equals 2x, so y equals 2/3 x. Now, just like before, you have a second equation that has x's and y's in it that you can work with here. So you're just going to go ahead and substitute that. When I substitute, I get x squared plus 4 times, instead of y, just like before, I'm going to get 2/3 x squared equals 7 plus 3x times, and again, instead of y, I'm going to put 2/3 x here. If we simplify this just like before, we get x squared plus 4 times, in this case, 2 squared is 4 and 3 squared is 9, x squared equals 7 plus, we have the 3's cancel, so it's just 2x squared. I'm going to move all the x squareds to one side, so I get x squared plus 16 over 9x squared minus 2x squared equals 7. I'm running out of room again a little bit. If I make a common denominator here, this is going to be 9 over 9. We've already got 16 over 9, and 2 is going to be 18 over 9. So if I add and subtract, 9 plus 16 is 25, minus 18 is 7. So I'm going to have 7 over 9, and it's going to be x squared equals 7, which means x squared equals 9, so x is plus or minus 3. Now, if I wanted to list my answers, my points are going to be two different points. The first point is when x is positive 3, and the second point is when x is negative 3. Again, I can find the y by just substituting, so 2/3 times positive 3 is 2, 2/3 times negative 3 is negative 2. And then if I want to write the equations of my horizontal tangent lines, these are both going to be lines that say y equals. In the first case, it's positive 2, and in the second case, it's negative 2. And I'm just getting those y values from the ordered pairs here. If I compare that to the graph, where would the tangent line appear to be horizontal? I'm going to guess right here and right here, which checks out. It's when x is 3 and y is positive 2, and when x is negative 3 and y is negative 2. All right, let's put it all together. So there are a couple more questions I just want to review with you that we've learned before, but that are often a part of these types of free response questions on the AP test. So consider the curve given by this equation. It can be shown that this is the derivative. So it's not saying show me how, it's just saying we know the derivative, this is it. First, we need to review that sometimes we're going to be asked to write the equation of the tangent line. Now, just like before, that means we're going to need a point, which we already have is negative 1, 1. We're going to need a slope, which we can figure out by doing the derivative and evaluating that at negative 1, 1. And we're going to use that to write the tangent line. So if I plug the 1 and the negative 1 into my slope formula here, I'm going to get 1 over 3 times 1 squared minus negative 1, which gives me 1 over 4. So my tangent line is just y minus 1 equals 1/4 times x plus 1. Just as a review of some of the other things we've learned how to do with implicit. Part B, find the coordinates on the curve where the line tangent is vertical. So we're looking for vertical tangent lines. Now, it doesn't say write the equations of the tangent lines, it just says find the coordinates of all of the points. So we're going to start by figuring out when the derivative would be undefined. My derivative is going to be undefined when the denominator, which in this case is 3y squared minus x, is equal to 0. In other words, 3y squared equals x. Now, x is already by itself here, so I'm going to go ahead and substitute that back into the other equation that I have that has x's and y's. So I'm going to have y cubed minus, instead of x, I'm going to fill in 3y squared, and then y equals 2. If I solve this, I get y cubed minus 3y cubed equals 2. So negative 2y cubed equals 2, which means y cubed equals negative 1, which means y equals negative 1, which means my points are going to be negative 1 comma something. Oh, sorry, not negative 1 comma something. Negative 1. There we go. I found my y. I didn't find my x. If you want to find your x, then what you're going to do is go ahead and plug that back into this equation over here. So if you plug in negative 1, you get that x would be 3. So your point would be 3 comma negative 1. That's going to be the place on this graph where the tangent line is vertical. And last but not least, find the second derivative at the point where x is negative 1 and y is 1. Now, in order to do this, there are really two steps, even though it doesn't specifically say that. First, we need to actually find the second derivative, and then we will plug in our numbers. So as a review, to find the second derivative here, we're going to need to use quotient rule. So I'm going to have low, which is 3y squared minus x, and then d high, which is dy over dx, minus high, which is going to be y, d low, which is going to be 6y times dy over dx minus 1, all over low squared. Now you'll notice that it never says here, find the second derivative. It just says evaluate this when x is negative 1 and y is 1. So the nice thing about this is because they're not going to really grade whether you write the second derivative in as simplified of a form as possible, we can go ahead and evaluate this without simplifying this expression. So in order to do that, here's how we're going to do that. D squared y over dx squared evaluated at negative 1 comma 1. So we're just going to plug in those numbers. So we're going to have 3 times the y is 1 minus the x is negative 1. And then dy over dx means the derivative with those numbers plugged in. Now, we actually already calculated that right up here. We got the derivative with negative 1 and 1 plugged in, which was 1/4. Minus your y is 1. And then you're going to have 6 times 1 times that 1/4 again, minus 1, all over, here you're going to have 3 times 1 squared minus negative 1 squared. And then we just need to simplify. Now, this is not easy to simplify, but the nice thing is we didn't have to simplify twice. It's not like simplify the derivative and then also simplify it again. We're just going to simplify one time. 3 times 1 is 3, plus 1 gives you 4, and 4 times 1/4 is just 1. So we're going to have 1 minus, now this is times 1, so 6 times 1/4 is 3 over 2, minus 1 is just 1/2. So 1 minus 1/2 over 3 plus 1 is 4 squared, which means we get 1/2 over 16, which is 1 over 32. And that would be your answer. All right, that is it for today's video. Thank you guys so much for watching, and I will see you for some practice.